Hello everyone, I'm Zhang from Huazhong University of Science and Technology. I'm currently in the fourth year of my PhD major in cloud cache optimization. So today I'm going to present OSCA, which is an online model-based cache allocation scheme in cloud block storage system. In this study, we first propose an efficient cache modeling method which can online obtain miss-ratio curve for each cache instance with a low overhead. Then, based on the miss-ratio curve, we can search for a near-optimal configuration and perform cache reassignment based on the solution. This is a work jointly done with my cooperators from Tencent company during my internship as part of the Intelligent Cloud Storage Joint Research Center of Huazhong University of Science and Technology and Tencent company. So, what I'm going to do first is to give you a research background about this cloud block storage system, hereinafter referred to as CBS, and then I'll present some analyses and observations which motivate us to design this OSCA system. And finally, we'll present some of the results and conclude this work. Nowadays, the CBS system serves millions of cloud disks in Tencent Cloud, and the total amount of storage has reached 100 petabytes, supporting the stable operation of millions of cloud virtual machines. Workloads of its service range from AI applications and medical applications. With such a large storage scale, the service performance is under tremendous pressure and challenge. The cache server is an important component for optimizing CBS performance. Cloud service providers typically employ cache servers, consisting of multiple cache instances competing for the same pool of resources. So, well-designed cache allocation policies play an important role in ensuring the stated service level objectives. However, the currently used even allocation policy determines the cache requirements in advance according to the preliminary offline statistics. This kind of static configuration method is inappropriate for the cloud environment and induce resource wastage. As shown in the left figure, the traffic is unevenly distributed to the storage nodes in the realistic CBS production system. In this picture, the color indicates the intensity of accesses. It means requests per second arriving at each storage node in 1 hour time window. The darker the red color in the figure, the more intensive the I/O traffic is. So, the cache requirement should be different as well. The red figure further shows a distribution of cache requirements of the above storage nodes in order to reach for a level of 95% hit ratio. The orange middle line in each box denotes the median cache requirement of these 20 storage nodes, while the top and bottom lines are the maximum and minimum requirements respectively. It shows each storage node has different cache requirements at different times. To optimize cache allocation, there have been proposed two types of solutions. One is quantitative methods, which are heavily dependent on reliable intuition or workload regularities. Therefore, their efficiency is not guaranteed for cloud workloads which are diverse and constantly changing. The other one is model-based policies, which are quantitative methods enabled by caching models, typically described by mixed ratio curves. The biggest challenge with quantitative methods is constructing accurate mixed ratio curves at acceptable computation and space complexity. Most cache models rely on offline analysis due to the enormous computation complexity and space overhead. So, a large number of research efforts have been made to cost-effectively construct mixed ratio curves to enable online mixed ratio curve profiling. In this study, considering the quantitative analysis method, we propose OSCA, a cache allocation scheme based on the online cache model. This scheme can search a near-optimal cache configuration with low complexity to maximize the overall heat traffic. Specifically, OSCA performs three steps. First, online cache modeling to obtain the mixed ratio curve. Then define the optimization target. And finally, searching for the optimal configuration. The left figure is the overall architecture of OSCA. It has no effect on the original I/O path, but add an additional cache controller to reconfigure the size of each cache instance periodically. Each cache instance is paired with a physical disk, which provides storage space for cloud virtual volumes. The cache controller monitors the access traffic to physical disks and construct mixed ratio curves to get the reassignment of cache resources among cache instances. The next step is cache modeling. The first step is cache modeling to get the mixed ratio curve, which plots the mixed ratio as a function of cache size. Existing theories have proved that the mixed ratio or equal to heat ratio can be calculated from discrete integral sum of reuse distance distribution. Specifically, the reuse distance is the number of unique data blocks between two consecutive accesses to the same data block. For example, suppose a reference sequence is A, B, C, D, B, D, A. The reuse distance of data block A is 3 because the unique data set between two consecutive accesses to A is BCD. For LRU cache, a data block can be hid in the cache only when its reuse distance is smaller than the cache size. So, the mixed ratio or equal to heat ratio can be calculated from discrete integral sum of reuse distance distribution. However, obtaining the reuse distance distribution has an O n times m complexity, where n is the total number of references in the access sequence and M is the number of unique data blocks of reference. Recent studies have proposed various ways to decrease the computation complexity to O(n) times log n. The most recent work shows further decrease the computation complexity with a fixed amount of space by sampling method. Different from previous works, in this study we propose real access ratio-based cache model to get the overall reuse distance distribution, which does not need to collect and process L traces with an O(1) complexity. Real access ratio is defined as the ratio of real access traffic to the total traffic during a time interval tau after time t. It essentially represents a metric reflecting how blocks in the following time interval are reaccessed. There is an example in the right figure. The number of reaccessed blocks during tau after t is 4, and the total traffic is 10. So, the reaccess ratio is 40% and the reuse distance of block X is 6. Therefore, we can get the overall reuse distance distribution by obtaining the reaccess ratio. The complexity of getting the reaccess ratio is relatively low. As shown in the right figure, we only need to look up the block request in a hash map to determine whether it is a reaccess request. From the definition, we can know that the reaccess ratio curve is a function relative to time interval t and time interval tau and timestamp t. Ideally, we want to obtain all the reaccess ratio curve at each timestamp t, which is cost ineffective. Fortunately, we observe that the reaccess ratio curve is relatively insensitive to time t by analyzing a week-long cloud block storage trace. Although cloud workloads are highly dynamic, therefore, in our experiment, we only calculate the reaccess ratio curve once a day to represent the reaccess ratio curve for the next coming day. Then, using the reaccess ratio curve and the time interval, we can estimate the reaccess ratio during 2 consecutive accesses of a data block and further calculate the reuse distance of this block. As shown in the right figure, to construct miss ratio curve from reaccess ratio, we first calculate the amount of data from the last reference of currently accessed block upon each block request by using the block sequence number, and then estimate the intermediate reaccess ratio using reaccess ratio curve. Then, we can get the reuse distance of the currently accessed block. This greatly reduces the complexity of analysis. Finally, the miss ratio curve can be derived according to the overall reuse distance distribution. With the above cache miss ratio curve, we then need to define the optimization objective function. Here, we consider our case being cloud server and cache, So we define the optimization target as reducing the access traffic of the backend storage. That is maximizing the overall head traffic. Now we have the miss ratio curves and the optimization target, and then we need to find a set of optimal cache configurations. That is to find a set of cache sizes for storage nodes to maximize the total head traffic. The simplest method is the time-consuming exhaustive searching, which will calculate all possible cases. To speed up the search process, we use dynamical programming. Since a large part of calculations are repetitive, a dynamical programming method can avoid repeated calculations using a table to store intermediate results and thus reduce its potential computation complexity to a linear level. Finally, it is our experimental results. To evaluate OSCA, we have collected 6-day-long L traces from a production cloud block storage system using a proxy server, which is responsible for I/O forwarding between client and the storage server. The cloud block storage system has served tens of thousands of cloud disks, and we are in the process of making it publicly available by the Sinner repository. In our experiment, the traces are saved in a network file system, and we have implemented a trace-driven simulator for the rapid verification of the strategy. We have compared OSCA with other 3 methods, including even allocation policy, miniature simulation with a sampling idea from shots, and the ideal case where exact miss ratio curves are used in placement of constructed cache models. First is the miss ratio curves. The figure shows the miss ratio curves of reaccess ratio based cache model, shown as a blue solid line with a cross, and the miniature simulation based on shots, shown as a green dotted line, and the exact simulation, shown as an orange solid line. This figure shows the results of 20 randomly selected but representative storage nodes. Other storage nodes have similar results. The above figure is the mean absolute error results. The mean absolute error of reaccess ratio based cache model is smaller than miniature simulation for 17 out of 20 nodes. We then compare the efficiency of OSCA in terms of overall hit ratio and backend traffic. The backend traffic is normalized to that of original method. From the figure, we can know that on average, OSCA based on reaccess ratio based cache model can reduce L traffic to backend storage server by 13.2%, and the reaccess ratio based cache model results in slightly better hit ratios than miniature simulation, except for hours from 48 to 60. Figure 3 shows OSCA adjusts the cache space for 20 storage nodes dynamically in response to their respective cache requirements decided by our cache modeling. The middle line in Figure C represents the average cache size for each node. It can be seen that the demand for cache space varies considerably between nodes, and our approach did respond correspondingly to meet the need at different times. So, in this paper, we propose an online model-based cache allocation scheme for CBS systems. Our approach complements the Scha's method, which uses sampling method but requires much less memory. We have demonstrated its efficiency by simulating experiments with real-world CBS traces, and we are in the process of making it publicly available by the Sina repository. Thanks for listening.